Yeah. Hello, everyone. Um, so uh, we are nearby the end of the semester. Okay. So we still have some sections left on chapter 7 and chapter 8. Okay. Chapter 8 is very short, so I think we can finish off. I hope the first week of January we can finish off all the chapters, and from the final exam, uh, I think the school schedule is from 11, starting from 11 January, uh, and we can decide later when will we have the final exam. Or do you have other course schedule for final? Not yet. Not yet. Okay. Because I want to have a one schedule, this class and the other class to be combined in in one big classroom. And I've checked most of your quiz results. Maybe only 3 or 4 left. Okay. So this Friday I will deliver the results to you, and the average is quite high. I think it's around 68 or 69. The average. The average. I think because I'm giving 16 points for bonus. And we already have 3 quizzes, right? So I think one quiz is left, one quiz left. Because we don't really have other schedules other than next week or the first week of January. So I want to have like the first week of January, we will still have a section and chapters, maybe chapter 8, but with a maybe more relaxed schedule. So you can study the other course also. So not really like not really complicated sections. So maybe the possible schedule, I think next week. And because next week there will be no class on Friday, right? Not New Year, right? So maybe the Monday class next week. So the last quiz will be about the chapter 6, the area and volume, area between curves and volume. And also the last part on at the Saturday class, I teach about the average value. Yeah, so only three of sections, 3 sections. So it's area between curves, volume, and average value. So maybe I will write for you. Okay. So quiz 4, chapter 6. This is area between curves. And then volumes or solids revolution. And the average value. Of function. So volume, you have 2 methods, the disk method and shell method. So quiz will be next Monday is 28th of December. So that's for quiz. So we will have the final exam schedule is actually from the 11, right? So from 11, 12, 13, 14, 15. I think this is Monday, Tuesday, Wednesday, Thursday, Friday. So I think I can ask you for maybe temporary schedule. So because I think because you don't have other courses scheduled for final now, but between these 5 days, do you prefer Monday or Tuesday, Wednesday? Which one do you prefer? Or any schedule is okay? Or do you have like obvious schedule for some courses? Maybe like chemistry or physics. That should be like obvious schedule. Usually they will take their obvious days, like in the course. Physics usually Tuesday. And how about chemistry? Okay. So maybe between Thursday and Friday. How about that? Between Thursday and Friday. And then I will ask the other class which they will prefer. Okay. And I will prepare the classroom. I hope I can find the big one, but if it's occupied, then I need to know the available schedule and then later asking you maybe through Moodle system. So maybe the best way is between Thursday and Friday. Final exam. Okay. Or if there is no other schedule, then maybe Saturday, maybe if there is no schedule available. Okay. But I think for now we can just select the Thursday and Friday. Okay. Okay. So next week quiz 4, and then final exam probably 14 or 15 January. So yeah. Okay, let me continue the courses. Okay. So last Saturday, I'm giving you the integration by parts. Let me just write the general expressions. So usually we write the u, dv, u, v, negative v du. So in integration by parts, okay, if you have the functions, for example, x sine x, dx, what you need to do, we need to select u and dv, right? Or the simple idea is select functions f and g, where f we need to derive and g we need to integrate from the whole integrations. Okay, and I also told you the simplify method of the integration by parts. Okay, so we can write di, or this is di, and we can write down all the possible functions that can be derived and integrated. And because we will have, okay, this is positive, this is negative, right? So we can write some arrangement in the table. Okay. So this is the u, the v, and v, and then du. Okay. So derive u become du, dv integrated become v. And what you need to do is this cross multiply, and This is UV minus V du. Okay, so imagine if you have the x sine x. This is d. This is positive, negative, and then deriving become 1. Integrated become minus cos x, and then add 1 more. It becomes 0. Integrating become minus sine x, right? And cross multiply. So this actually the whole thing becomes negative x cos x. It's negative 1 multiplied by negative sine x become plus sine x. And then actually this is, you need to multiply 0, and it should be this if you want to write the whole thing. But because it's 0, then we can remove this and we can add plus c. Okay. So this method, if you have learned before, this is called the DI method, and it's actually the integration by parts, but with some arrangements, table arrangements. Okay. So that's the review for the integration by parts. Maybe you want to write down first. And the second sections after the integration by parts is trigonometric integrals. Let me write in the new page. Okay. So trigonometric integrals. I've told you a few parts. We learned the sine, mx, cosine, and x dx. And it depends on m odd or n is odd. The idea is to have the odd one. For example, if I have sine 5x cos x, okay, dx, okay. So we need just to find which one is the odd one. Okay, it's the cos or sine. I think in last Saturday there's I think 1 or 2 students asking what if the other one. The other one is it doesn't matter. It doesn't matter. So the idea, if for example this you see it's having odd number 5. Okay, what you are going to do is we need to make this odd one become an even. So we need to separate. Okay, so first let me separate become this. Okay, and the sine 4, it can be written as, let me write here, sine squared squared, right? And the sine squared we can change to 1 minus cos squared x. Okay. So by doing this, we can use substitutions. U is cos x, because when we have du, it's negative sine x. And we can change all, and then we can cancel this sine x, right? And then maybe adding negative here. So we will have a good arrangement of 1 minus u squared, and then u, and then du. And then you can solve the substitutions with u. So that's the first idea. So trigonometric integrals is integrations using identity in trigonometry. Okay. the identity is where this first one is sine squared x plus cos squared x equal 1. So it can happen in sine or cos. Okay. So in this case, you are using substituting the cos x with u. Okay. If it's happened in the odd one is happening in cosine, then you can substitute the sine instead of cos. Okay. That's the first case. Okay. Sine and cos. Okay. Okay, now the second case is tangent and secant. So of course, if we are involving secant and tangent, you need to write or use the tangent squared plus 1 equals secant squared x. Okay, and you can substitute later. Okay, the idea is still similar with sine cos, but you need just to change the basic trigonometric identity with tangent and secant. Okay. For example, let me give you the tangent 5x and secant 7x dx. Okay, the idea for tangent and secant. Okay, if you are going to use substitutions later, then you need to consider which element you need to cancel, right? Because you want to cancel later in substitution. So it's better if you imagine if you have tangent x and secant x and try to derive this. Right? Tangent x deriving become secant squared x. So the second one is secant x tangent x. So our goal in tangent and secant is finding the secant squared or secant x tangent x form in order to be cancelled. Okay, right? And then that way we can consider which element we want to substitute. Okay, which u we need to substitute from the expressions. And if you carefully see, okay, because we have this form here, okay, the idea for which one we need to separate, okay, because it's involving secant and tangent, and we have this is tangent squared and secant squared. The idea is making this odd number 5 and 7 become even number. Okay, become even number. Okay, so we can separate the tangent 5 become 4. Okay, and secant 7 become 6. Okay, and we can write down the other part, secant x tangent x dx. Okay. Now, if we see the tangent 4 here, it's actually tangent squared and then squared, right? And then tangent squared is secant squared x minus 1 and then squared. Okay. So we can write secant squared x minus 1 and then secant 6x and then secant x tangent x dx. Okay. Now, it was, I think, obvious because we now have the secant x tangent x, which is the form that came from derivative of secant, right? So secant x tangent x, we need to cancel this. So we choose the u is, let me write here. So u will be secant x. So you will have u minus 1 and then squared, and then u, and then with power of 6, and then du. And du is secant x tangent x dx. And then the rest, I believe, it's doable. You know, to expand the quadratic and multiply by the u with the power of 6, and then later change back to secant x. Okay. Okay. I'm giving you the other example. So what you need to do is manipulate the form and find which one between tangent and secant you can get easily the squared, because you want to have tangent squared plus 1 equals secant squared equations to be substituted. Okay. Okay. Let me give you another example for the tangent. Okay, tangent 6x and then secant 4x. So again, the idea is to choose in which tangent or secant, it's 6 and 4, which one between tangent and secant can be manipulated into the squared. Okay. I think it's easier for the secant. Secant 4 is secant squared and then squared, right? So let's change the secant. Let me write this become secant squared, secant squared. Okay. Now we need to relate the tangent and secant, and we need to write the secant squared is tangent squared x plus 1, right? So at least we have tangent 6x and then tangent squared x plus 1 and then secant squared x dx. Now you have secant squared for canceling, to be cancelled, right? So we need to write down the substitutions is tangent x, because when you derive, it will be secant squared x dx. Okay. And then you can cancel the secant squared. And the whole equation becomes u6 and then u squared plus 1 and then du. This becomes u8 plus u6, and then we can integrate u8 and u6. It's become 1 over 9 tangent 9x plus 1 over 7 tangent and then plus c. Okay. Now let me write the official explanations. So there's two possibilities. First, if secant is even, n is equal, even number is 2k. So any multiplication 2, okay, of a number. So tangent mx secant, let's write 2k x dx. And let me write 2k become secant squared x, and then let me write k minus 1, and then secant squared x, okay, dx. And then later we can substitute. U will be tangent x. Okay. And let me write the second one. The second one is if tangent is odd. M is 2k plus 1. So every multiplication by 2 and then plus 1 is become odd number. So tangent 2k plus 1x secant and x dx. So this becomes tangent squared x and then k, and then secant x, secant n minus 1 x, and then secant x tangent x. This is the first example that I gave you. We separate the secant and tangent so that we can substitute the, or let me write this tangent become secant squared x minus 1, and then we can substitute u with the secant x. So I think that's it for trigonometric integrals. So we only have variation in sine, cos, and tangent and secant. So actually, trigonometric integrals is basically using the trigonometric identity, and then later using the regular U substitutions method. So actually, the method in integrations actually is only two. Okay, the other part is just a combination or variations method. Okay? So the general method is only the substitutions method, and the other one is the integration by parts. So only two really important method in integrations actually. The other part is just a combinations with the substitutions, combination with the integration by parts. So I think if you are having a good analogy to understand the trigonometric identity, I think this should be not really complicated. Okay. But if you have problem with trigonometry, I think you can review the trigonometric parts. Okay, the next section is called the trigonometric substitution. Okay. So it's substitution method, but we are substituting the trigonometric functions. Let me write here. Let me write it's trigonometric substitutions. So meaning we are substituting a variable with trigonometric functions. Okay, let me give you just an example on how this is happening, and then later at the very end I will conclude what we are doing. So let me give you the integrations. And then dx. Okay, now to solve the integrations, we are now seeing that it's have 1 over x squared and then square root x squared minus 9. Okay. So the key point in trigonometric substitution is you're seeing the square root here, right? And you're seeing now x squared minus 9. Okay. We have at least 2 trigonometric identity: sine squared plus cosine squared plus equal 1. And then the other one is tangent squared plus 1 is equal secant squared. Okay. So let me write the identity first. Okay. And see if you understand. So let me write sine squared x plus cosine squared x is equal 1. Okay. We can write this, right? And we can write this. And the other one, we can write tangent squared plus 1 equals secant squared. So we can also write tangent squared as secant squared x minus 1. Yeah, I think only this one, I think. Yeah. So you may have, okay, a constant minus cos squared here, are variables, right? A constant minus also a variables. And here, variables minus a constant, okay? Or maybe a variable plus a constant and become the secant squared. Now we see the question is a variable minus a constant, right? So it's similar with our secant squared minus 1. Okay? So the idea is we can set, okay, we can set this x, okay, we can set this x as 3 secant theta. Okay, we can set 3 because it's from 9, square root is 3, right? So the idea is we are substituting this x, and then we can simplify the equations under the square root. Okay, so let me write the expressions. It's become 1, and then 3 secant squared is become 9 secant squared theta. Okay, and then let me make longer, and then square root 9 secant squared minus 9. Okay, or I'll write secant squared theta minus 1. Okay. And then don't forget we have the x is 3 secant theta tangent theta d theta. And we need to also write this in our equation. Let me write on the top equations. So 3 secant theta tangent theta and then d theta. And then secant squared minus 1 is tangent. This is become tangent squared. And then 9 tangent squared. Square root is become 3 tangent. Okay. And let me cancel this, become 3. And secant. So let me write this as tangent theta over secant theta, and then 3 secant 3 tangent theta. Okay. Now this is canceling this. Now it's 1 over secant. It's becoming cos theta d theta. Okay. And I think 3, 3, oh, 3, 3, and this will be 1 over 9. Okay, 1 over 9. Let me write in the front. So this 3 and then 3 from tangent. So 3, 3 become 9. So this becomes sine 1 over 9 sine theta. Okay. But it's not over yet. Okay. I need to still plus c, but I will do that later. Sine theta, because it's theta, and the question is actually in x, right? So we need to changing to x. Okay. So we need to change to x. Let me draw the triangle. Let me make theta here. Okay. And we know that secant theta is x over 3, or cos theta is 3 over x. Okay. From our definitions and the assumptions. Okay. So cos theta is 3 over x, so it's 3 here and x here. And the other part will be x squared minus 9. So sine theta becomes 1 over 9 x squared minus 9 over x, right? And then plus c. And that should be the final answer. And also notice that the theta is an angle in a triangle. So that should be defined the domain of theta. Okay. The domain of theta. I will later write the domain. So the theta, it couldn't have more than, or if you see the square root, it cannot be negative, right? If you want to have real number. So the theta need to be positive. So maybe you remember sine having positive in which quadrant in polar, okay? And that will be the domain to become the positive one. Okay. Okay, that's the first case for the trigonometric substitutions. So we are explaining the 1 over x squared square root x squared minus 9. Okay. And this is the solutions. And actually, you can use trigonometric substitutions in any uh, in any functions actually that can be solved. But sometimes maybe it will make the solutions complicated, but still doable. Still, you can use it. Okay? But in particular, for this square root here, okay, the square root here, it's actually better with the trigonometric substitutions. I believe. Can you use other method? I don't think so, because the square root is making the whole integration difficult. The square root. Yeah. Maybe you can use the integration by parts, but I don't think it will be easy solution. Yeah, I believe the only quick solution we have is by trigonometric substitutions. Okay, the next one, let me give you just the example first. Let me write here. It's x cubed and then 9 minus x squared dx. Okay, now we have, so the idea of trigonometric substitution is you need just to look at the square root, okay, the square root. Before we have the variables minus a constant. Now we have a constant minus variable, right? So it's, I think, either sine or cosine, because both of them is 1 minus sine squared or 1 minus cosine squared, right? So you can use both of them. You can choose sine or cosine. The result should be the same, or similar, okay? Because we have a constant problem with sine and cosine. So you can choose cosine or sine. But here I will just choosing the sine, okay? X is 3 sine theta, okay? And write the dx is 3 cos theta d theta. And change all to the theta. Now x cubed becomes, let me write 3 sine theta and then cube and then square root. It's 9 1 minus cos squared theta, or sine squared theta. And then the last part is dx is 3 cos theta and then d theta. And then this become cos squared, and this become 9 cos squared, and then we square root the 9 cos squared becomes, let me write this, it's become 3 cos theta, so it's become 3 cos theta. Let me write that, and making this here. So I now have 3 power 3, and then 3 multiplied by 3. I will be combine all with the 3, become 3, 5. And then we have sine cube, and then cos squared theta d theta. Now we have trigonometric integrals from previous sections. So the idea is finding which one is odd number. It's sine, right? Cube. And then we can separate this. So separate becomes sine squared. Or let me write this is sine squared. And this become sine squared become 1 minus cos squared. Okay, now we have more than one problem. Okay, so first we substitute with trigonometric functions. Later we have the trigonometric integrals. We solve the trigonometric integrals and become this. And obviously, the integration can be solved by u substitutions, right? From the trigonometric integrals, we can substitute cos theta with u so that we can cancel the sign, right? And we solve this first. And then later, at the end of results, we can substitute back to the x. So let me write this. So it's 3, 5. Let me write minus. And then 1 minus u squared du du. So this u squared minus u4. So it's become 1 over 3 minus 1 over 5. And this is, let me plug in the negative so we can 1, 5. But let me write this first. And then you can use theta here. Sine theta is x over 3, which is here. And this side will be 9 minus x squared. So cos theta is square root of 9 minus x squared over 3. And okay, this become complicated. So 9 squared divided by 3 and 5. Wait. And then minus 1, 3. And then 3. Okay, let me write in a new page. Write in the new page. So become 3, 5. 1 over 5. Let me write the 9 minus x squared. This is 5 over 2. This is 3, 5. Minus 1 over 3. 9 minus x squared. And then 3 over 2. And 3, 3. And then bracket. And then plus c. So we can simplify the solutions, I think. This 3. Yeah, I think this is the final answer. Okay, any questions first? Okay. The last example for the trigonometric substitution. Have integrations x cubed. Okay, now it's under the square root, we have variables plus constant, right? Now, the only way to get the variable plus constant is imagine the tangent squared plus 1 is secant squared, right? Right? Because there is no other way. If we choose between sine, cosine, secant, tangent, and it will be easier if the squared become tangent. If you have tangent squared plus constant, it will becoming the secant squared, right? And you can square the secant squared easily. So x will be and then we can substitute 3 tangent cube. And then this becoming 9, 1 plus tangent squared. And then 3 secant squared theta d theta. And this is become a secant squared. And 9 secant squared become 3 secant theta. And now we have 3 tangent cube. This is canceling. So 27. And then we have tangent cube theta and then secant theta, d theta. And again, this is the trigonometric integrals problem. We have tangent, which is odd. We have cube, right? We have cube here. So what we are going to do is we separate tangent squared and then secant theta and then tangent theta and then d theta. And this tangent squared become secant squared theta minus 1. And then we can let du is equal secant theta. And then du will be secant theta tangent theta d theta. Okay. So 27 integrations u squared minus 1 and then du. It's 1 over 3 secant cube theta minus secant theta. Okay. We are not done yet. We need to use the triangle. So tangent theta is x over 3. So this x 3. So this become 9 plus x squared. And the secant is 9 plus x squared over 3. Okay. And we need to substitute all to the equations. So 27, 1 over 3 9 plus x squared, 3 over 2, 3 minus and then you can solve it. I think this become 1 over 3 minus 9 squared of n plus c. Okay. Okay. Any questions? No? After the sections, we will move to the partial fractions. Okay, but before I'm going to partial fraction, I think I will moving to partial fractions this Friday. So I think I will give you some I think interesting integrations and the, some solutions. Okay. I think if you want to just go to the toilet, I'm giving you maybe 1-2 minutes. And by the way, this Friday you will have the presentation, right? For introductions, right? Okay. Yeah. Okay. Now I have integrations from 0 to x. The formula is square root of a squared minus t squared dt. Okay. Now, from our previous trigonometric substitutions, we can let the if a is constant. Okay. If a is constant. If a is constant. And we let the t equal a sine theta. Okay. Now we can simplify the solutions for any case if you have this kind of square root and then a squared minus t squared. So dt will be a cos theta d theta. Okay. Now we can write this become a 1 minus sine squared theta, and then writing a cos theta d theta. Okay. This become cos squared theta. And this become a cos theta. Okay. Or I will write this as or let me write the final conclusion is a squared cos squared theta d theta. Oh, and the integration point becomes, because it starts from t0 and t is x. Okay, so if t is 0, theta is also 0. And then if t is x, then the theta should be, well, let me write this sign. So sine theta is t over a. So theta should be sine inverse of t over a, right? In terms of x, this become 0, and the other part is sine inverse x over a. Now we still have, this is 0, this is sine inverse x over a. Okay. Now we have a squared and then cos squared theta. And what we are going to do is we are using this trigonometric identity. Okay, I think this will be helpful in some integrations. Okay. You can use, let me write all possible, it can be 1 minus 2 sine squared, and cos 2 theta is also can be right minus 1. Okay. Now this cos squared theta is cos 2 theta plus 1 over 2. And I can write this. And because a is constant, I will write a outside of the integrations and over 2. And this is sine inverse. And this is 0. And this become 1 plus cos 2 theta and then d theta. And then we can integrate. This become theta plus sine plus sine 2 theta over 2 from 0 to sine inverse of x over a. And we have a squared over 2, and we input all the endpoint. So this becomes sine inverse x over a plus sine 2 theta, and input the sine inverse. Let me write this become sine theta, or let me write this first, okay? So you will be, let me write this first. Sine theta cos theta from 0 to sine inverse x over a. Now, before substituting the sine inverse, let me define the Okay, let me define the triangle. So sine theta is t over a. Or in this case, it's becoming x over a. Okay. Now, cos theta will be a squared minus x squared in square root and over a. Now we can write this as sine inverse x over a, and then plus x over a, and then cos theta we can write directly a squared minus x squared a. Okay, and then the other part is all 0, right? So minus 0, and then we can write this as half a squared sine inverse x over a plus half x square root a squared minus x squared, and this become some formula. Okay, so you have integrations. Okay. Notice that if you plug in the sine inverse to theta, it's become the sine inverse. Plug into sine theta, sine inverse is x over a, and cos sine inverse is become the cos theta, which we define in the triangle, and we can simplify with becoming the square root of a squared minus x squared divided by a, and we now have some formula that if you have square root and then a constant squared minus t squared, you can plug in directly to this formula. But even though it is applicable and the formula is applicable, um, to be honest, I'm not suggesting you to memorize all this. Okay, at least you get the idea that you have the square root, you have some constant squared minus t squared, and you can use it for some formula to define the integrations. Okay, and you will have some sine inverse there. I believe if you are using the cosine, you can also do this similar things, and you can have some another formula for this case. Okay. Okay. I think I'm giving you some practice example, and for partial fractions, I will start next Friday. Okay. So let me give you some examples. Okay. The first example is secant inverse. Okay, secant inverse. Do you want to try by yourself? Secant inverse. Yeah, I think the integrations is basically, like I said in the early courses about integrations. Integral is more complicated than derivatives because you need to think backwards or reverse. And if you are if you check on maybe some video on YouTube, uh, there are regular competitions about integral in MIT. So every year they will have like a committee member in the, I don't know, maybe some kind of like a student association there. They will hold like uh, annual competitions. I believe it's called B integration MIT. You can check the website. B like a bee, honeybee, integral MIT competitions. And their questions is really difficult. And so the competitions is start like a tournament. So each of the students or who want to participate, they will have like a number, and they will have like a drawing. And then after they get the number, they will set like who will fight who. And then the judges, they will write the questions at the front. The question is just like integral of some functions, and then they will need to write down the answers. And the fastest who can write down the answers, uh, he or she will be the winner. And they will have like compete like all the participants until the finals. And it's just like crazy. Like some questions is like if you are solving it through like regular writing, you need at least several minutes. But like one or two students, they write like you cannot really see their solutions, but they just need to write down the final answer, and then he write the final answer, and okay, the winner, and he got the winner, and then it is like a nerd, right? Like nerd. And then the viewers or the audience, some audience they bring their laptop and they're using some software to calculate the questions and to make sure the question is correct. So yeah, like a bunch of nerds. I don't know. Is there any similar competition in Taiwan? No. Is there any similar competition? Maybe other university? I haven't heard. I haven't heard. But yeah, you can check. And I think several also in YouTube. You can also check some YouTubers. They try to answer the questions from that competition. And yeah, some questions are really uh, like you cannot even integrate with any method you have. So you need to think with other way. Maybe if I have time, I can show you maybe one or two examples that I can understand, because most of them I also cannot understand easily. Okay? Okay, now the secant inverse. Okay, uh, anyone solve this? No. The short review, or the short possible answer to solve this secant inverse is this using integration by parts. Okay, because we already done secant inverse in derivative, right? In derivative. So maybe let's check the derivative parts. Okay, maybe we check this first. Review our derivative. Okay, so we can use the let the some theta is equal to secant inverse. Okay, so we can have the secant theta is x, right? So we can have at least first relations in the triangle with the secant theta is equal x, right? So secant theta is from the triangle. So this is theta. I believe this is x and 1, right? Because cos is 1 over, yeah. So you have the other side's value will be x squared minus 1, square root, right? At least you're having this relations first. Okay? And in derivative, we are derived this and using the implicit differentiation, right? You are differentiate all of this become with the ddx, okay? Secant theta become the secant tangent. And then we have d theta over dx. Let me write maybe here. Okay. And actually, we want the d theta over dx. Okay, we want this to be our solution. So this is 1 over. Let me write the secant. The secant theta is x, okay, and then the tangent theta is these sides, right, over 1. Okay, so tangent theta is x squared minus 1. Okay, so the secant theta tangent theta I will substitute 2 with the x and square root of x squared minus 1. So x and then x squared minus 1. Okay, and this is actually the form that we want to write if you want to derive. Okay, if you want to derive the secant inverse x. Okay, or let me write the ddx. Theta is secant inverse x. Then this is the answer. Okay, now we have this, right? Now, if we have the integrations and we want to use the integration by parts, we can use the secant inverse as our function that can be derived. Okay, and dx will be the other part. Okay. Now, let me just write maybe here. So if you have integrations secant inverse x dx. Okay. We can write this as, or let me write, move to the left a little bit. I can write this as x secant inverse x, okay, minus it's x, and then the other is this, right? Okay, get it? I can write the integration by parts like this, okay? And I can cancel this, cancel x, and now I have 1 over square root of x squared minus 1. Now we already did this square root and then having squared inside, right? The x squared minus 1, the trigonometric substitution. And we can use that to solve this. Okay. Now we can use the x is secant, right? Is secant theta. Okay. I think this is really nice, right? Really nice. So we already defined that. So it should be and then we can solve this. Integrations. It's become secant squared minus 1 become tangent squared, and then square root become tangent. Okay. Become tangent 1 over tangent. And then secant theta tangent theta d theta. And then I can remove the tangent, and I will have secant theta d theta. And we already did this secant theta on Saturday, and I already upload. I think I have upload or not the secant. It will be the ln, right? Let me write here. Ln secant theta plus tangent theta. Or we can solve secant theta become x based on our definitions, and tangent theta become x squared minus 1. And then we can solve this. So the whole answer will be, or let me write the secant inverse x dx is equal x secant inverse x minus ln plus 1 and then plus c. Okay. And because it's plays really nice, it's the settlement is really good here. So whenever you have maybe besides the secant inverse, maybe you have x squared, you can also change this into that x squared. Okay, and then maybe you will have another integration process. Okay, so you can have another maybe x squared, x cubed, or maybe another terms. Okay, but if you have ln x secant inverse x, that would be a little complicated, because ln x you can think the derivative part, and secant inverse you also think the derivative part is easier, right? So I think that will be really complicated. I haven't tried that, but maybe I will try, and then maybe if that is really interesting, then I can show you how. But I think ln x secant inverse x, that's possible. That's possible because we know the integration secant inverse, and we know the integration of ln x. We can use this integration by parts. Okay. I think it will be more, at least four elements. I think four. Yeah, four. If you have ln x here, but if you're just having any polynomial, easy x squared, x cubed, I think it will be similar like this. Similar form. Okay. So I think I will stop until this explanations, and then Friday we will have the other sections, the partial fractions, and also we still have additional schedule on Saturday, this Saturday. So sorry for any activities that you might hold on that day. Maybe Saturday you have some activity. Okay. And also next Friday, New Year, no class. Okay. No class New Year. Yeah. So we have holiday on New Year, but not on Christmas. Sorry. Sorry.